Untitled. Okay. All right, so we're going to start with an iron wire demo, and you should have received that already. Okay, so this is the phase diagram of iron. That's what we'll be talking about today. So let me just enlarge this a little bit. So can everybody see back there? Somewhat? All right, let me see if I can get this out of the way. I have to move this over. There you go, just so I can move this down a little bit. There we go, and then we'll move this back. Okay, now we can do this. Okay, so this is the iron phase diagram that we left off at. The x-axis has pressure, and the y-axis is temperature. Okay, so we live on Earth, and right now it is 1 atmosphere, so we're about 1.01 bar, so we're here-ish, okay? These are our conditions. So we'll just move up in temperature on this phase diagram. So Janet has her personal protective equipment on, as you can see. And so what she's going to do is she's going to start by increasing the temperature. So this is going to resistively heat the iron wire. Okay, and so what you see here is you should see the iron wire. I don't know if you can see in the back, but there are some magnets that are attached to the wire. They're round magnetic balls. And then there's also a weight hanging off of the wire that's in the middle. And for visualization for the back, it's attached to a hot pink plastic ball. Okay? So now we're just going to talk about your observations as Janet, you're a very dedicated TA, by the way. Janet has recovered from a grave and prolonged illness. So she's here, we've tested it, so you know, your instructional team has rallied. So what she's going to do now is increase the temperature by increasing the voltage on this variac right here. And so what do you think we're going to see as we increase the increase the temperature? What are the possible observations? It could have, yeah, but the wire is going to get hot, specifically the antecedent of it. Okay, so there's a proposal that the wire is going to get hot, which is exactly what I said, so thank you for listening. Anything else in terms of physical phase transformation?
It'll get longer.
Okay, the wire could potentially get longer. Why would that be?
Because the molecules are getting energy from the heat.
Okay.
So
The molecules are getting energy from the heat, so there's some sort of energy transfer. Okay. What else can we say about the density or the phase that the iron is in? Yes?
I think it's around 500. The crystalline structure rearranges, I think, from FeC to UCC iron.
Okay, so why do you say 500?
I saw this before somewhere.
Okay. So the answer is I saw this before somewhere, so it's 500. So if your memory doesn't serve you correctly, the best way is just to read off of the phase diagram itself, right? It gives you all the information that you need, and those in the front may or may not smell a smoking smell. That potentially is the oil that's coming off, because if we don't coat the oil, if we don't coat the wire, the iron wire will easily oxidize and become iron oxide, and as we know, that's rust. And it will be brittle, and then it will just break. So if you smell that, don't worry, it's just oil burning off. Probably okay for you. Yeah, so here you just read off of the phase diagram. So here you go from alpha, or BCC, okay? There's a phase transformation from alpha to gamma, and the phase diagram says that's 910 degrees Celsius, okay? There's also something that's particular to iron. It is a ferromagnetic material. So I think some of you may be familiar that it is magnetic in some way, right? It's ferromagnetic, so all the spins are aligned. At some point, those spins, once given enough thermal energy, will do exactly this. My hands are waving in the air, right? So you will lose that ferromagnetism. But when does that occur, right? Well, we can take a look at it. So Janet, why don't you ramp it up? And Janet is going very slowly as to not heat too fast. Try to aim for the Curie temperature as best you can. Okay, so it's getting hot. Maybe there's too many magnets and they're hanging on to each other.
Well, it's cooling. The magnets are cooler.
Yeah, so I think you might have to, you might have to get to the point where it's above the Curie temperature. Okay, so she's going very slowly. What do you think will happen to the magnetic balls that are attached to the wire once the wire loses the ferromagnetism? I heard, either way. I did, what? What's your name again? Okay, so Solomon said the magnets are going to fall once it loses the ferromagnetism. So that's right at the Curie temperature, right? So what's not on your phase diagram, because it's talking about thermodynamic, for dramatic effects, they were. I'm really glad the magnetic balls are getting the applause. I think it's actually for you. Right, so as predicted, I think I heard some murmurs over here as well. Right at the Curie temperature, we call that TC specifically. That's the Curie temperature. At 770 degrees Celsius, the iron wire loses the ferromagnetism. So at room temperature, we know it's going to be BCC, as denoted in the phase diagram, okay? And now Janet has gone to beyond 7C, so it's still BCC, right? Between 770 and 910, where this phase transformation will happen, that I'm outlining in black right here, all right? It's still BCC, because you've seen a magnetic transition, but the crystalline phase has not changed yet. There's an asterisk to this. There's a bit of controversy whether or not there's a beta FCC. But yeah, it's a whole thing. For now, just take it as it's still BCC, okay? All right, now what do we see? The wire is red hot, right? That's incandescent property. All right, so, and the original prediction is that it's going to lengthen, okay? And now let's try to cool it slowly, or you can kill it too. Yeah, let's go slowly. Okay, so now as it cools, it's a little bit more difficult to see once the weight has been dropped. But what you should see is a contraction, right? So, okay, so beyond 910C, all the way up to 1394 degrees Celsius, according to the phase diagram, it's FCC. Okay, so there's been a solid-solid phase transformation. But your eyes it's going to be difficult for your eye, the human eye, to pick this up. The hot pink ball was supposed to be an aid, but it dropped, so there you have it. But let's talk about what one should expect to see in terms of the length of the wire as a function of temperature, and also the height of the weight. And I'm going to, this is positive, this is negative, this is negative, this is positive. Okay, so the original hypothesis by Monica in the front, thank you, has said that it's going to lengthen. The wire is going to lengthen as you increase in temperature. Okay, that's the general trend. And then at some point, we saw magnetic balls drop, so that's the Curie temperature, right? That's denoted as TC in the community. And then we haven't experienced a phase transformation yet, so I'm just going to draw a dashed line just to help the eye. So then it's still BCC. What you have here is just thermal expansion, right? The lengthening of the wire is due to just heating up the wire, and there's thermal expansion. And then at some point, you're going to hit the transition temperature going from alpha to gamma, right? BCC to FCC at 910 C. But what's the difference between BCC and FCC in terms of density? Yeah. Yeah, so the answer was FCC is the answer, denser than BCC, okay? So this density is going to be less than that of FCC, and if you actually look it up, it's about 7.87 grams per cubic centimeters, and so this is denser. It's about 8 grams, I think 8.5 actually. Grams per cubic centimeter, 8 to 8.5. Okay, so it's denser is the point. Yes? Why? Why is FCC denser than BCC? I'm just talking about the density itself. So when one can do this with X-ray diffraction, you can just take the iron, and at room temperature, you can just do XRD, and you know what the crystal structure is. And it's BCC. And then at high temperature, it's FCC. It just is, which is an uncomfortable and unsettling answer in engineering, I realize, as part of the scientific method. So I think it's perfectly all right to be unsettled, because there are some things we don't know, and we continue to strive for that knowledge. But it's denser. I think you may also notice something curious. It goes back to BCC once you increase beyond 1394. I don't know. But let me get back to your comment about being denser. So if it's denser, then you would expect a contraction, right? And that's actually what you see, well, what you could have seen if the ball was still there. It's a little bit of a subtle change, but so actually, let me erase this because it's not supposed to be part. So here's another transition, but now it's a phase transition. It's a crystalline phase transformation from BCC to FCC. So you'll notice a bit of contraction, so the length will decrease a little. And then through thermal expansion again, one would expect the wire to expand once it's in a different phase. Okay, so then upon cooling, the reverse will be true. Right, you'll see, I'm going to change color real fast, just so you can see it a little bit better. So if you follow the yellow highlight, the reverse should be true, right? That you should see a contraction, and then a lengthening, and then a contraction, right? In these specific regions. Okay, I saw a question, but let me get, okay. I guess that question was answered. Okay, so that is it for the demo. Any questions while your fabulous TA is cleaning up the demo? 1, 2. Correct. These were just magnetic balls that we bought at the craft store, and we just attached it to the ferromagnetic iron. Yep, and then they dropped once you lose ferromagnetism.
I was going to ask to see it melt.
You were going to ask to see what?
To see the wire melt if you raise the temperature.
Yes, okay. The question was, can we see the wire melt? Yes, but then that would ruin our wire. But yes, you can absolutely melt it. What's going to happen, of course, is the heating is not going to be even, and at those kinks where it starts melting first, eventually it's not. You're going to disconnect and lose your circuit. Anything else? I think that's about it, right, Janet?
Yeah, the other reason we don't melt the wires, we don't burn the room down.
That too. We don't want to burn the room down. This is a classics building, Near Eastern Languages and Civilization building. We'd like to keep our colleagues where they are.
I mean, another example that there's a change that's occurred
Yes, thank you. Thank you for that reminder. So Janet mentioned that the wire is much more brittle now because there's oxidation. So what you can't see there, or possibly even here, is that there's a little bit of dust, black dust on here. That's the wire that is oxidized, and that rust is now falling onto the table, which we will clean up for the next class, okay? So yeah, over time, the more times we run this demo, the wire will get brittle and it will just crack, yeah.
Does it regain its magnetic properties?
It does. So the question was, does it regain its magnetic properties? Absolutely, right? Paramagnetism at high temperature, go down below the Curie temperature and you'll get back ferromagnetism. Absolutely, yeah. The magnetic structure is reversible. So that's a whole nother field, magnetic structure. We won't talk about that. We'll just talk about magnetism, but not the magnetic structure itself, which is how the spins align. Yeah?
Did you say that it lost its magnetism once the unit cell switched from BCC to FCC?
So the question was, did I say that the wire lost its magnetism once the material went from BCC to FCC? No. The magnetism occurred, the loss of ferromagnetism to paramagnetism occurred at 770 degrees Celsius for this material. The phase transformation from BCC to FCC occurs at 910. So they are related, but in this case, one does not, it's not related where, in the sense that it doesn't have to be at the same temperature. Your magnetic transition can be at a different temperature than your phase transition, because it all has to do with the spins, which doesn't have the spin of your iron centers itself. Like each iron atom has these electrons, right? Those electrons, how they align with each other in the unit cell, that's a whole different topic. So magnetism and magnetic structure isn't always, no, what I mean by spin is your electron has a spin up and a spin down, right? So if they're all spins up like this, that's ferromagnetism. If they're spin up, spin down, because that's just how they are, then that's anti-ferromagnetism, and that's a whole different topic. We will get to magnetic properties in a little bit, but that doesn't have to do with necessarily inducing a BCC, FCC, if that's your point. Okay. Any other points of clarification? Okay. Thank you very much, Janet, coming back from the prolonged illness. So I appreciate that. Okay, so we are going to switch over back to our slides. And if this cooperates, how are we feeling here? We're looking good. Let me adjust the light so that you can see a little bit better. Oh, thank you. If you can just hit stop. And I should probably take this or else I will forget it here. Thank you. Okay. Good enough. Okay, phase diagrams. We've talked about equilibrium in many ways through that demo. And so we'll talk about all of that in an extended phase diagram. And so where did we leave off last time? We left off at discussing, the single component iron phase diagram. So let's go over to Top Hat and discuss which of the following statements are true, right? Is it that the phases shown on the diagram correspond to the lowest free energy of the system for the indicated temperature and composition values? B, metastable phases cannot be found on phase diagrams. C, it is possible to transform one solid phase into two other solid phases upon cooling. Or D, a given phase shown on a phase diagram has one and only one discrete composition. So let's switch over to that. Okay, so let's see, let's present. when we talk about equilibrium and phase diagrams, which one of these statements are true? Oh, gosh. Yeah, it's okay. Feel free to confer with your neighbors. And then we'll wrap up in about 10 seconds or so. Okay, last 4 individuals. Let's get your answers in. All right. So, let's take a look at what you answered. Okay, so the majority of you do agree that the phases shown on the diagram correspond to the lowest free energy of the system, right? That's what it means to be in equilibrium for the indicated temperature and composition value. Okay, that's great. And only some of you said that metastable phases cannot be found on phase diagrams. That is false. So metastable, that is true. Metastable phases cannot be found because when we're talking about equilibrium, we're talking about what is the equilibrium phase, right? So if something is metastable, that means it's not stable. It could be stable under some conditions, but that's not what we're talking about, right? We're talking about equilibrium. If we wait long enough, if we get to a temperature and we wait long enough, what is the equilibrium phase, okay? So that's a particular note. And then it is not possible to transform one solid phase into 2 other solid phases upon cooling. That's false, right? We absolutely can form 2 different phases when we cool. Currently, up until this point, we talked about a phase. We talked about solid solutions, one phase of a solid solution, but you can have multiple phases, absolutely. And then a given phase shown on a phase diagram has one and only one discrete composition. That's false, okay? So let me see why it's not showing the correct answer. There you go. That's false because as you recall on the phase diagram itself, the x-axis is composition, right? That means you can achieve multiple compositions for a 2-component system from 0 to 100%. Whether it's weight percent or atomic percent, okay? So there's no one discrete composition that we'll be talking about. We can talk about multiple compositions, okay? And then your phase fractions will be different. So the takeaway message is when you look at a phase diagram, we're talking about equilibrium phases, okay? All right. So with that, I'll come back to this. Okay, so what other information can one get from a phase diagram? We talked about the x-axis being composition, right? How much of A are you putting into B? That sort of thing. We can talk about the temperature. Well, which temperature are you at? In the demo, that's what we talked about, right? Are we in the BCC phase field? Are we in the FCC? That was dependent on temperature, which temperature we were at. And of course, we were dealing with a single component system, so we were just going through different phases of iron or different allotropes of iron or different polymorphs of iron. It's all saying the same thing, okay? Okay. So when you have something that looks like this, it can be as simple as what we were talking about, just iron or H2O. You can have things that combine solution phase and solid phase. Okay, so in this particular example here with brine, if you're not familiar with brine, that's salt in water. Okay, you probably have seen it around the November time frame when everybody seems to have an opinion on how to brine their turkey. But brine is just some sodium chloride or salt in H2O. So you could read off a phase diagram for NaCl in water the same way, right? So in the x-axis, you have here, okay, that's definitely pen. You have here a pen that does not work. Okay, so here we go. So yep, that seems to work. Seems to be A-okay. Let's see. You have to switch over to pen. All right. Yep, let's see. Well, folks, it appears that the pen works of sorts. Let's see. Okay. Well, you may just have to follow my my mouse if that's the case. Okay, I think you just have to follow the laser pointer until the pen decides to cooperate. Okay, so let's talk about the phase diagram of NaCl in H2O. So here you see you can go from 0 to 100 weight percent of NaCl, and at, let's say, 25 degrees Celsius, which is room temperature-ish, you see that you could add NaCl in 10, 20, I'm reading off of the x-axis, 30 weight percent, and then you hit a solubility limit, okay? At this point, you're going to get two phases. Here you have brine, which is NaCl in H2O, and then you can also have some salt that will start crashing out of the solution, all right? And that's NaCl, the salt crystals that you think about. It's just going to fall to the bottom. Okay, and at a different temperature, let's say you're below the freezing point of H2O, let's say you're at negative 10 degrees Celsius, you're not going to have water, right? H2O will now take the form of ice, and then you'll have some salt water in it, in this phase field. Okay, so you can see we can deal with phase diagrams for solid states that we've been talking about, but we can also deal with it in solution phase as well, okay? And here's another example that's in your book. It's the sugar-water phase diagram. All right, so here you have one phase. It's just liquid. We call it syrup, but it's just liquid of sugar in water. As you increase the temperature, as you increase the composition in weight percent sugar, you hit the solubility limit where you'll still have some liquid phase of sugar in water, but then you also get a secondary phase, that's the solid sugar that's just going to start crashing out because it's saturated and you can't put any more sugar in there at a certain temperature. So let's say you're at 25 C here. The solubility limit is 65 weight percent of sugar. And you probably have seen this, right? When you're trying to make lemonade or just putting sugar in water, you've observed the solubility limit. So we can do the same thing for the solid phase, except now we're putting in just another component that is in the solid state at a certain temperature. And above a certain temperature, depending on what the phase diagrams say, you could be in the liquid phase. All right, so same concept, just now with different materials, okay? So we talked about phase diagram, solubility limits, a solution. We talked about, obviously, the solution that you probably think of every day, liquid form, but there can also be a solid solution. And then if you have mixtures of these phases, well, we just call it a mixture. We call it what it is, okay? Okay, so where can you move on this map? You can move in X, you can move in Y, right? So if you're moving in Y, you're changing the temperature. And if you're moving in X, you're changing your composition. Here, you're changing the weight percent of NaCl, okay? So changing in temperature is just going from point A to point B. Changing from, in composition, you're increasing the weight percent of NaCl, and that's going from B to D. Okay, and we call that, the composition that you're at, let's say A, B, we'll call that C naught. So when we talk about the composition of a system, we call that C naught. And you'll see it over and over again as we go through the different phase diagrams. Okay. I've talked about this. In the interest of time, I'll jump to the Gibbs phase rule. Okay, so when we talk about phase diagrams, we also want to know what are the degrees of freedom. What can we do to the system if we want to maintain, let's say, if we want to maintain the number of phases, the same number of phases, or what have you. So there's what's called the Gibbs phase rule, and it tells us the relationship between the degrees of freedom, so things that you can change in the system, and where you are in terms of the number of phases that you have, so that's P, and the number of components that you have, right? So if you have metal A and metal B, or ceramic A and ceramic B, or polymer A and polymer B, you have two components, okay? So that would be your C. C would be equal to 2 in that case. So then you can calculate what F is through the Gibbs phase rule. And here it's F equals C minus P plus 1. 1 can also be what's called N, N being the non-compositional number, right? So what can you change? So in the phase diagram that we'll see, if you're at a certain composition, you can change the temperature. So N is 1. So that's what we're going to be talking about. You can if you can change the temperature, and you can change the pressure, say, right? Non-compositional variables, then N would be 2. So to be clear, this number would be 2 if you could change non-compositional things like temperature and pressure. That's 2 things that are not composition. But for the next series of examples, it's going to be 1 because we're just changing the temperature, right? We're changing one variable that is not the composition. So let's work that out. If you see a phase diagram that looks like this, it's called a isomorphous binary alloy phase diagram. So that means you're mixing in component 1 or component A. And the second component, let's call that B. So if you're here, right, the number of components that you have is 1. You just have B because you have 100% of B. Okay? But you could potentially have liquids and phases. So your P is 2, as denoted here, and you're changing temperature. The y-axis is temperature. So your degrees of freedom is 0. What does that mean? It means if you move off of this point in any direction, you're no longer at the melting point of B. Right? If you want to stay at that point, you have 0 degrees of freedom. Okay? And the same thing for this point over here, where you have 0% of B, but 100% of A. So your component is 1. Everywhere else, between A and B in the x-axis here, is a varying composition of B. So you're changing B, going from 0 all the way to 100% over here. Okay? So there, your C, or your component, would be 2. You have some A, you have some B, so your C is 2. But in this region, we'll talk about phase fields in a slide, but in this region, there's only one phase. And in this region, there's only one phase. They're colored differently. And so your P is going to be 1 in either of these 2 regions. But in this particular region right here, there's going to be 2 phases. Okay? So let's dive into that. How would you even know that? Well, let's talk about it. This is a more detailed version of an isomorphous binary phase diagram. So iso is the same, right? Morphous meaning it has the same structure. So for this particular example, we've talked a lot about copper and nickel, so let's talk about it some more. We discussed with the Hume-Rothery rules that copper will form a solid solution with nickel, and vice versa, right? They're both FCC, they have similar atomic radii, their electronegativities are the same, their valences are the same, so they're going to form a solid solution. So you can go from 0 to 100 weight% of nickel in the copper matrix, and at whatever composition that you're at of nickel and copper, in this blue region right here, it's going to be one solid phase, okay? One phase. It's going to be what's called the alpha phase. So you'll see this time and time again, right? With the iron, alpha iron is BCC. But here, this alpha phase, it's now FCC. So alpha is not always one particular crystal structure. We call everything alpha because alpha is A, and we start our alphabet that way, okay? So if we have to start naming things like phases, we just start with the beginning of the alphabet. Okay, above this line, this curved line right here, it's called the liquidus, and above that line, everything in your system is going to be liquid, and everything below the liquidus line, solidus line is going to be solid, and the phase field that's in between right here is going to be some mixture of liquid and solid alpha. Alpha in this case, we know is FCC because we know nickel and copper are FCC. If you didn't know that, all you would know is that it's alpha. Okay? Yes, question in the back.
For that middle section,
Mm-hmm.
what was the percent composition of the liquid and solid phase?
So the question was, for the area that's in the middle, will the composition of the liquid and the alpha be the same? No. And so you bring us to the next topic, which is the tie line. Okay, so before I talk about tie line, I just want to point out this is the melting point of copper. On the right side here, where the red laser is, that's the melting point of nickel. Okay. Okay, so actually before I get to the tie line, how do you measure this? You can actually measure the temperature. You can reproduce this phase diagram by melting together copper and nickel and just measuring the temperature over time. And then if you plot the composition, temperature as a function of composition, you can map out that area that we saw in white in green right here. Okay, so you can just put it in a pot, control the temperature and the environment, and you can track this and make the phase diagram. And that's what people used to do, is this is how we know all of this information. There was an entire group of people who like very carefully did all of these measurements, okay? So let's talk about that tie line and that, okay, so I did fix this on the other computer, but a number of challenges have shown themselves today. So let's talk about that tie line. Let me get to that. So here's a tie line. So you draw an isothermal line. Let's say you're at a composition that's right here. Okay, so let's get to that example. Let me fast forward to that. Okay, here we go. Here's a good example. So I fast forwarded to your question. If you are at 35 weight percent, so C naught is 35 weight percent nickel. All right. If this is what's in your system, you have 35 weight percent nickel and 65 weight percent copper. Right? 100 weight percent now. That's your system. To answer your question, the composition of how much nickel is in the liquid phase versus how much nickel is in the solid alpha phase are not the same. And you can determine them by drawing this isothermal tie line right here. Okay, so you mark where you are, but how do you know that you're here? Well, I said, for the sake of this example, we're at 1250 C. You could easily be at a little bit over 1200 C. Let's say you're right here. That will change the composition of liquid, so Cl and C alpha will be different, but C naught is not different, right? So if I'm just going up and down in temperature right here, I haven't changed C naught. I haven't changed the amount of nickel that's in my system. I've just changed the temperature. And when I change the temperature, I change where I am in terms of the tie line. I change the isotherm. Right? Here it's 1250 C, here it's a little bit less than 1250 C, here it's getting closer to 1200 C. Okay? So you could see that that changes your tie line. That changes the amount of phase fraction of liquid to alpha, and thus it changes the amount, because where it touches the liquidus and where your tie line touches the solidus tells you what Cl is, the amount of nickel that's in your liquid phase, and C alpha, the amount of nickel that is in your solid alpha phase. Okay? So, any clarifying questions in regards to that? I've said the same thing a number of times in different ways, so hopefully it's sticking. Okay? But your C naught hasn't changed. The composition of your system hasn't changed. Cl and C alpha change because where your tie line touches the solidus, when you read it off of the x-axis here, you could see if you move along the solidus, right, your C alpha is going to change. And I would write all of this down on your slide if I had a pen. You would think amongst 3 devices, we would cease to have this problem 3 weeks in, but here we are in life, so bear with me, okay? Okay, so you can mathematically work out why this is. I mean, if you've ever been on a seesaw, right, you know that the heavier person, right, will be lower to the ground. So if you want 2 people to be at the same height, you can just change the weight, or you can change the center of mass, right, where you put the middle, where you put the anchor of the seesaw, which you can't do as a 5-year-old, I realize, but you can imagine doing that for this, okay? So if you have Cl here, C naught and C alpha in your tie line, right, if you take the fraction of y, the length, so C alpha minus C naught, divided by the total, which is C alpha minus Cl, if you do that, you get the phase weight fraction of L, which is over here. And then correspondingly, you can calculate the weight fraction of your solid by C naught minus Cl divided by the total. Okay? And you can mathematically work out why it's the opposite distance if you go through all of this. Okay, in the interest of time, I'm not going to go through the algebra, but you're basically just moving variables around until you get the final equation. Okay. Okay, so what I just did was what's called the lever rule. So if you're given a C naught, if you're given a composition of the system, in this case, how much nickel do you have, how much weight percent of nickel do you have in the system, you can calculate, if given the temperature, what is the CL, as well as what is the C alpha. In this case, it's the solid, where it touches the solidus line. And you can figure out the phase weight fraction. Okay, so how much liquid do you have in your system? Well, at 35 weight percent nickel, that's your C naught, you draw the tie line, and it intersects the liquidus, Cl, at 31.5 weight percent nickel, and your C alpha is 42, so you read it off of the x-axis here at 42.5 weight percent nickel. And then if you plug it in, you get the weight fraction of liquid is 68%, and thus the weight fraction of your solid is 32%. So right at 35 weight percent nickel, 1250 C, you have 68% of your system still in liquid form. It hasn't fully solidified yet. And then 32% is in the solid form already. It's already started to solidify, right? So let's go through that. So you're in the liquid form, right? You're still in liquid in the green region, and then you hit the liquidus line. Some of your system, some of your material is going to start solidifying, and then you're going to get some alpha, but the majority of your material is still in liquid form, right? It's still in the liquid phase, and you drop the temperature down some more, and if you happen to be at 1250 C, you can quantify how much liquid you have and what is the weight fraction of solid that you have, right? So you can track the amount that has solidified just based on the phase diagram. Question?
Yeah, that 68.3%, that's the temperature factor?
Yeah, yes, that's exactly at 1250 C. Let's say you're at 1249 C. That will be different, right? So it has to be at a certain point, right? So I'm talking specifically about C naught equals 35 weight percent nickel, and temperature is 1250 C. These two numbers, WL and W alpha, the phase weight percent for, the phase weight fraction for liquid and solid happens to be alpha. That is exactly for that composition. Yeah, so it's all based on the tie line and the lever rule.
So liquid is solid at 12.
Yeah, it exists because you're right here in this region, right? Both liquid and solid alpha exist right here. Let's say you drop the temperature down some more. Let's continue. If you drop the temperature down to here at, let's say 12, we eyeball it, about 1200, a little bit above 1200 C, you're going to get 100% alpha. Right below the solidus line, everything is alpha, right? Okay. Yes?
So is the phase weight fraction comparable to like the quality factor for like a phase transition between like a water, like compressed liquid and then vapor, like vapor phase transition? But this is like solid to liquid. Is it comparable to that?
I don't know.
Okay.
But we can talk after class. Okay. So I've worked out some more examples here. So this is just a chart of where you can track everything. So we can track what I just talked about, point A, point B, and point C, and you can get it all worked out to where you're in the liquid region, liquid and solid, and then all solid. Okay, so all of that. In the interest of time, I want to just talk about this entire table. It's a lot of numbers. Yes, but you have all the equations worked out where you can practice for yourself and make sure you understand this table right here, how you get all of these numbers, and also work out what's called the microstructure. We'll talk more about this later on because it is the motivation for why we even need phase diagrams and why we want to track how much of each phase we have. Because the next time that we talk, we'll talk about particular points where you can get a depression in the melting point if you mix A and B in certain amounts. That's called the eutectic point. And that microstructure will be quite different than, say, someplace else in the phase diagram, and that will determine your mechanical properties, okay? So here, let's talk about the microstructure for copper and nickel. So here, if you're in liquid, right, we draw the microstructure that looks like this, okay? This dark green is just all liquid, okay? And then at 1260 C, you start to get some nucleation, right? That's a little bit below the liquidus line. This dot, I know, looks like it's a little bit above the liquidus line, but it's below the liquidus line. So then you get to have some solidification here. So these are the blue dots that you see, okay? So here you start to get some solidified alpha that come out of the liquid solution. And then at point C, what we just talked about, right, the amount of solid you have increases. So the weight fraction of solid increases. And then you drop the temperature some more. You're slightly above the solidus line. So you still have some liquid green. And now the amount of alpha solid that you have has grown even more so. And then eventually, when you're in E, you have an entirely solid system. So it's all alpha, all blue. And this black line right here, and right here, and right here, and right here, that's to indicate the grain boundaries, right? When we talked about polycrystallinity in imperfections, right, we talked about how grains can orient themselves in whichever way, unless you're trying to grow a single crystal, like in the Bridgman method or the Tchaikovsky method, right? If you have a polycrystalline material, you have grains oriented in whichever direction. So that's what it's representative of, is that these alpha grains are polycrystalline, and that's what you have if you're just dropping down the temperature and it's isotropically cooling. Okay, we're going to pick up on eutectic phase diagrams next time.